Hello, Professor Stambach. For our final lab project, we decided we wanted to know how a Leyden jar works. So first things first, what is a Leyden jar? The Leyden jar was first invented in 1745 by Ewald G. von Kleist. This German experimenter made the Leyden jar to study electrostatics, and with the Leyden jar's capability of storing electric charge, it's essentially a capacitor. Now, unlike the diagram shown, we had to make some modifications with the materials that we had. For our version of a Leyden jar, we use a thin plastic bottle wrapped with aluminum foil. Inside the bottle is water with salt, and at the top is a ping pong ball wrapped in aluminum foil where the discharge will be seen by the accompanying wire. To better understand how the Leyden jar works, here's David with the explanation.
Okay, so the way our Leyden jar works is that we're going to be rubbing a PVC pipe against our cloth. In doing this, we're using friction to create static electricity. The PVC pipe is going to be stealing electrons from our cloth, making the cloth positively charged and the PVC pipe negatively charged. Once this is negatively charged, we're going to be rubbing the top of our Leyden jar onto the conducting sphere. This is placing our electrons that we just stole from the cloth onto the conducting sphere and into our Leyden jar. In doing so, it is pushing the positive charges onto the outside of our conducting plates, causing us to discharge it with our wire to the top. Because this is positively charged, and this would be negatively charged. Typically, if you want it to be more conductive, you would want to ground yourself, and you would want to ground the conducting, the Leyden jar as well. In doing so, you are then, whenever your positively charged cloth is becoming positively charged, if you're grounded to earth or against your wrist, your cloth would be stealing electrons from earth, becoming neutral again, which allows you to steal more electrons, placing them back onto the Leyden jar. And if our Leyden jar was also grounded, the excess electrons that are on the outside of our conducting plate would be sent to earth, making this more positively charged on the outside. In doing so, you would just be essentially just pumping charges into the Leyden jar, creating more and more of a charge on the inside. Unfortunately, we were having problems with our grounding, so we didn't go that route, but that's typically how you would do a Leyden jar.
Thanks, David. As mentioned in our attached abstract, we manipulated the number of strokes and amount of salt for each trial. For the first trial, or the trial with 1 tablespoon of salt, here are the results. As you can see with each succeeding video clip, the discharge increases with more strokes to the PVC pipe. Next, we wanted to compare trials of different amounts of salt. Instead of showing all of the video clips for each trial, we figured our experiment would best be illustrated by each trial's 50 strokes attempt, which is the strongest output of each trial. For good measure, here's a zoomed in frame of the 50 strokes clips side by side. Finally, we wanted to know which variable influenced the magnitude of discharge the most, the amount of salt or the number of strokes. So, we chose a middle ground, or a baseline if you will. This frame is from a 2 tablespoon trial at 30 strokes. We then compared it to the trial with 1 tablespoon, but at 30 strokes and at 40 strokes. Like the previous comparison, the trial with more salt had a larger discharge than the one with lesser salt at the same stroke count. However, we can see that the trial with 1 tablespoon of salt at 40 strokes has a larger discharge than the 2 tablespoon trial at 30 strokes. After finding this out, we added a frame of a 3 tablespoon trial at 30 strokes. Initially, we thought that the amount of salt had a greater effect on the jar's discharge, but as we can see here, the 1 tablespoon trial at 40 strokes still beats out the 3 tablespoon trial at 30 strokes. Even though there's a 2 tablespoon of salt difference, since the 1 tablespoon trial at 40 strokes, which is 10 more strokes than the 3 tablespoon trial, it has a larger discharge than all the trials with a lower number of strokes. Using this data, we then went on to create our graphs. Since we measured the discharge by using our eyes, we judged the magnitude from each trial on a scale of 1 to 8. We felt that this scale accurately measured the discharge because we believed that within each trial, there was a 1.5 increase in magnitude after each attempt. This means that there is a 1.5 difference between a 10-stroke attempt and a 20-stroke attempt. We use 1.5 because we also had to factor in the fact from before that the number of strokes influences the magnitude of discharge more than the amount of salt. As you can see in this graph, the succeeding 1 tablespoon attempts are always greater than the previous 3 tablespoon attempts with lower stroke counts. To summarize our findings, we found that within the same stroke count, adding more salt will produce a larger discharge. But when comparing attempts with different stroke counts and different amounts of salt, we found that the number of stroke counts better influences the magnitude of the jar's discharge. If we were to do this experiment again, or if someone were to replicate it, we advise that instead of measuring the discharge visually, the help of an instrument that can measure the jar's discharge will yield more accurate results.